Okay? So this is hidden. This is the rotor, right? It's on 2 bearings also. This guy is called a coupler. And this coupler allows some misalignments. It transmits torque, but it does not transmit the bending, because this will not be perfectly aligned, right? To exaggerate, this is the motor, and this is the load. Okay? This is the real world situation. Of course, you try your best to align it. But if you exaggerate the situation, it's like this. And so what I need here is I need some method of coupling that will allow this misalignment. And there are many different types. Okay? So, one other reason why you use a coupler. This is the load, right? There will be some unbalance, meaning like the fan is not perfectly symmetrical, and so it'll vibrate. Of course, you do your best to balance it, but in the real world, no perfection. So there is some vibration here. It will be taken up by the bearings and by the ground. Ground meaning like the casing. You don't want that vibration to transmit to your motor, or otherwise your motor will be broken. So this is also why you have couplers. The coupler also separates this vibration from the load to the motor. Okay? Do that later. While I'm on it. Okay, so these are the different ways you transmit the torque from the motor to the load. There are some common ways to transferring the torque. There are keys, splines, set screw, pins, press fits, or tapered fits. So, I want to get to the coupler. Yeah, this is called a shaft coupling. Okay, the motor is attached to the shaft coupling via certain ways. In this case, it's called a set screw. Okay, this is an Odom, I think that's what they call it, or spider. This is a spider coupling. So this is one side. This is plastic, and this is the load side. And there is some clearance. So you see, this spider actually allows some clearance while transmitting torque. Assembled is like this. So if you rotate this guy will follow. But there is some gaps here. There is some gaps to allow for that misalignment. This is a rigid coupling. It does not allow much misalignment, but maybe some clearance between the set screw and the shaft. There is some play. Okay. This is another shaft coupler. These are cuts. Okay. These are cuts, so it actually flexes. This is called a flex coupling. So it allows this while rotating and transmitting. So let's look at some videos on that. Shaft couplers.
One mode.
coupling is a device used to connect two or more machine shafts for the purpose of transmitting power. There are different types of couplings, and the types of couplings you choose will depend on various factors, such as the horsepower or load of your machine, the torque, or the shaft size. There are two basic types of couplings to choose from: rigid and flexible. Flexible couplings, as their name implies, can flex slightly, which allows them to tolerate a small degree of misalignment. This is the most common type of coupling in general industry. There are several types of flexible couplings, including elastomeric, disc pack, and gear couplings, each used for a number of different reasons. Rigid couplings are used when large amounts of torque are transferred, often found on modern industrial machinery, such as turbine generators. Four things to keep in mind when it comes to couplings are: sizing. Couplings must be sized for proper horsepower, torque, speed, and environmental conditions. Installation. If the shaft diameters and coupling bores are not machined or sized properly, machine components could be damaged. Alignment. Even though flexible couplings can tolerate some misalignment, precisely aligned machines will run longer, smoother, quieter, and will require less downtime. Maintenance. Coupling should be inspected and lubricated if needed on a regular basis. Remember, just because a coupling can tolerate a certain amount of misalignment, other machine components may not. For this reason, shaft alignment tolerances are based on the entire machine's health, not just that of a shaft alignment.
Okay, so there are two types of misalignment. We'll talk about that. There is something called angular, like what I've drawn, and the other one is offset. That's when you have two shafts that are parallel, but they are offset.
Tolerances are based on the entire machine's health, not just that of a coupling insert. Couplings are often viewed as simple machine components, but sizing, installation, alignment, and maintenance are critical for long-term, trouble-free operation of the machine on which they are used. For more...
Okay. So, let's watch a bit more videos on it, different types and shaft alignments. Okay, so let's look at this. This gives
movement, or
this gives a disassembly of the spider coupling.
a coupling is a device used to connect two shafts together at their ends to transfer power. Their primary purpose is joining two pieces of rotating equipment together while permitting some degree of misalignment and movement, or both. Couplings are most commonly used to transfer power from a motor to a pump, connect shafts of two machines manufactured separately, provide mechanical flexibility, prevent shock and vibrations from transferring from one piece of equipment to another, and potentially slip when torque overloads occur.
Okay, so he mentioned a few things, right? One is allow misalignment. Second is isolate the vibration from the load to the motor while doing all this while transferring torque. There are also torque limiters that can break, like a fuse. Think of it like a fuse. If something goes wrong, the torque couplers break and your motor is not harmed, the load is not harmed. Say you have like a spiral transporter to transport sand, for example, and then a big rock comes in, and so your load basically locked up. Your motor will be stuck, but this allows some slippage. Some couplers do allow that.
They typically feature two rigid parts that fit around the ends of two shafts to form a sleeve. A hub sits between the teeth to provide the buffer between each coupling half. Flexible couplings provide similar results, with a one-piece aluminum body designed to shift under differential torque loads. Stay tuned to Galco TV for more tech tips.
Okay. Let's look at shaft alignment concepts. this is, let's watch this final one for coupling types.
The coupling I have here is the zero backlash type OC Hold'em coupling. This is a good all-around flexible coupling when you're looking for a coupling to provide homokinetic transmission and to exert low reactive forces under large radial misalignment. One of the things we really like about this coupling is its machined midsection. By machining the midsection instead of injection molding it, the part has a higher torsional stiffness and a longer service life. The type UA. This is your go-to coupling for low torque, light-duty applications when you're expecting large angular and radial misalignments. The type UA can handle up to 0.05 inches of radial misalignment and up to 6 degrees of angular misalignment. Basically, it's similar to a classic Oldham coupling, but it handles those angular misalignments like a universal joint. The plastic bushings you see here also act as a grease reservoir and provide smooth flexion and zero backlash. And, because they're mounted within a machined metal midsection, the UA can transmit much more torque than most flexible couplings.
You guys know what backlash means? Okay. This handle, ideally, when I start to press on it, it rotates the mechanism, right? But there is usually some gap. So there is some gap where I'm not doing anything. So this motion, this little motion here, does not rotate the latch. So this is called backlash. Okay? Most mechanism has it. Because if you don't have it, then you have preloading and everything is tight and everything can break easier over a lifetime. So some backlash is always there, but you want to minimize it. This coupler sometimes add a little bit more backlash. Can you see? If I allow some clearance in that plastic, then you have some rotation where you are not actually turning the other side. So from this shaft to that side, like I can move a little bit but not rotate the entire assembly, right? So this backlash can create problems sometimes. So there are couplers that are zero backlash.
Next, we have the type BC, a block coupling. Yes, they are still out there. The block coupling is obviously not a new design. Essentially, it's an Oldham coupling with grooves in the hub instead of the mid. Not many manufacturers are still making block couplings because it's easier to produce a conventional Oldham coupling. The type BC's midsection is large enough to house an internal grease reservoir, which makes it especially useful for dirty or harsh operating conditions. The type SC. The jaw coupling or spider coupling is a common choice amongst designers as a general flexible coupling, despite the fact that it's not very flexible. It doesn't accommodate very large misalignment, and it exerts strong reactive forces when the two shafts are misaligned. The primary purpose for going with the type SC jaw coupling is its torsional dampening capabilities. In addition, though, it also provides a high peak torque rating, and it's machined from bar on CNC machining centers with live tooling. That's a nice feature when considering how poorly machined hubs can lead to bores that are off-center with respect to the spider, which obviously causes misalignment issues from the start. The type UJ universal joint handles misalignment of up to 45 degrees and has a uniquely designed yoke to increase strength and minimize stress concentration. As with the other couplings, the UJ has no powdered metal components. It's made with 17-4 stainless steel and 70-75 aircraft aluminum with a low friction coating. All of this makes for a very strong joint with zero backlash. And last, but of course not least, OEP's rigid coupling. This coupling makes the most sense when you're expecting little or no shaft misalignment. The coupling has a low moment of inertia, maintains a constant angular position, and of course, it is CNC machined with live tooling, so it can handle very close tolerances. To find out more, visit the...
Okay, so let's look at shaft alignment concepts.
Shaft alignment know-how. The basics. Misalignment of the shafts causes vibration in both machines. This will damage the bearings, seals, coupling, or other machine components. Good shaft alignment allows machines to run more efficiently, reducing power consumption while increasing output. Let's look at how it's done. Very common rotating machines in industry are pump and motor sets. When a motor runs, the shaft rotates and transmits power through the coupling to the pump. Because alignment is so important, tolerances were developed to define the most misalignment you can have and still be okay.
So this table shows you for certain RPMs, this is the allowable misalignment. As you can see, higher RPM will require tighter or more accurate alignment, naturally speaking, right? Because then you're having more fluctuations every second.
We will explain about these tolerances in a future video. If this was a 3600 RPM motor, these would be the tolerances. Forget for a second that we are aligning two machine shafts. Instead, imagine two simple lines that represent the shafts. The goal of an alignment technician is to adjust these two lines to be collinear. Collinear means that two lines are positioned as if they were one single line. In the real world, we aim to align the machines as collinear as possible within tolerance, at the coupling or point of power transmission. Typically, the machines will be misaligned in two ways and in two dimensions. Let's visualize this. Vertical and horizontal. Both vertical and horizontal directions each have a combination of offset and angular misalignment. To measure, we rotate the shafts to find the relative positions between the two center lines of rotation. Once we know the misalignment, we can correct it by adjusting the movable machine vertically and moving it side to side in the horizontal plane. If we get the two rotational center lines to be nearly within tolerances in these two directions or planes, then they will be nearly collinear and therefore properly aligned. The process of precision alignment can be broken down into three simple steps. First, measuring and inputting the machine dimensions. Second, measuring the misalignment between the shaft center lines of rotation. And finally, calculating the necessary corrections and aligning the machine to be moved. Shaft alignment know-how. The 5-step procedure. When we perform a shaft alignment on any machine, we should all follow a set procedure. Following, we present Ludeka's recommendation for a simple and effective procedure for doing shaft alignment. First, we perform the pre-alignment checks, safety procedures, lockout and tagout of the machines, visual inspection of the foundation, grout, and base plate, cleanup, remove rust, scale, paint, and dirt from the bottom and around the feet.
So the way you adjust vertically is using shims. Okay, these thin plates are called shims. They're shaped like this. So this is where the bolt is, okay? And then the reason for the opening is so you don't have to literally take it apart, right? You can go from the side and slide it in, and this tab you can pull it out. So they come in different thicknesses, and depending how much you need to adjust, the engineer usually have a collection of shims, you know, this thick, this thick, this thick, and then depending how much you want to adjust, and then you put all these shims. That's how you adjust vertically. Horizontally, then you'll have to rely on some clearances on the holes on the foot. Or if it's on a plate, there is a nut on the behind. Sometimes the plate has like slotted holes or some clearance where you can adjust a little bit. I'm not going to finish the video, but I do want to show the concept of run out. Run out. You use something what is called a dial indicator. Oh no, still no quality.
Runout is caused by a bent shaft or by eccentricity of the coupling. Eccentricity literally means being off-center.
Hold on, I know there is a better quality video than this. Chef, no, not better. Sorry.
Off-center. It can occur if the coupling is not bored in its physical center, or if the bore is bigger than the shaft, and the set screws pull the coupling out of center. When measuring runout, the dial indicator is mounted to a fixed point in space.
Okay, now the watermark is disturbing me. Hold on. Wait. Maybe this is better.
Mounted perpendicular to the shaft. Eccentricity in a rotating object, typically a shaft or a cylindrical part. It is a measure of how much an object wobbles or deviates from its ideal axis of rotation. Runout is caused by a bent shaft or by eccentricity of the coupling. Eccentricity means to be off-center. It can occur if the coupling is not bored in its physical center, or if the bore is bigger than the shaft and the set screws pull the coupling out of center.
So sometimes set screws can do this, and that's why when you have set screws to tighten a shaft onto something, you gotta make sure you tighten it kind of on a star pattern, so you're not pushing it only to one side.
A dial indicator, or the Accolem runout probe, can be used to measure runout. The runout probe is a digital version of a dial indicator which connects to the pre-alignment application and calculates total runout. The runout probe is what we will use in this video for demonstration purposes. When measuring runout, the probe base should be mounted to a fixed point, such as the base of the machine or any other fixed position. We recommend that you first check for runout at the hub or the rim of the coupling, because there you will pick up both eccentricity and bent shaft. Some people will also measure runout in the axial direction, which in addition would tell you if the coupling bore is skewed. Before taking the readings, make sure the plunger is mounted perpendicular to the shaft. The plunger can both expand and contract, recording negative and positive values. These values correlate to the high and low spots on the shaft. For this reason, when mounting the probe, it is important to set the plunger to half its specified travel range. This assures the probe can measure its full capacity in both positive and negative directions. Once the probe is affixed, rotate the shafts. It is best to rotate in only one direction. As the shaft rotates, the probe determines the total amount of runout. The pre-alignment application takes the difference of the minimum and maximum values to calculate the total runout present. If the runout is within acceptable limits at the hub, usually 2 thou or less, then the coupling must be bored properly and the shaft is reasonably straight and within acceptable limit.
2 thou is 2,000ths of an inch. Americans like to say that. Thousandths mean 0.001.
In this case, the probe is indicating excessive runout of 22 thou. When excessive runout is observed, we next need to determine if it is being caused by a bent shaft, an eccentric coupling, or both. We achieve this by repeating the same measurement process at the shaft. You'll want to take the measurement as close to the coupling as possible. In this case, there is 21 thou of runout at the shaft, accounting for most of the 22 thou of runout we observed at the coupling. Therefore, the bent shaft is the problem. If our measurement of the shaft had been close to 0, the problem would have been the eccentricity of the coupling. Of course, we could observe a situation where both conditions occur, a bent shaft and an eccentric coupling. If excessive runout is present, it should be corrected before attempting precision shaft alignment.
Okay, so you do this before you do an alignment. This is called a dial indicator. Have anyone used this before? No?
Out of change.
I'm showing this because this is a manual version. That one was a digital. I use this sometimes on a brake rotor where you resurface a rotor and you want to know whether it's wavy or is it perfectly flat. And so you touch this, you rotate this, and then take this thing and observe. You touch it and then you observe the plus and minuses along the as you rotate it in the angular fashion. Yeah, right. So the movement in this needle
Which equals the total amount.
corresponds to the run out. See? Because it wobbles.
If the runout
Right?
is within acceptable limits at the height, 2 thou or less,
It's not bad. Yeah. So that's shaft alignment. There are laser alignment tools also. Okay, I'll let you take a break, and then when you come back, we'll cover some of the slides that I skipped, and then we'll go from there to an in-class exercise. Okay? Take like 10 minutes. 10 minutes break.
Emang intinya males tuh, udah mulai
Tunggu banget.
udah mulai males sih. Semenjak kita berbeda fakultas nih, kita berbeda jadi berantem nih. Kita udah mulai lost connection. Mungkin gimana? Kita beda jalan. Setelah kampus gue pada so bahkan
What's the WhatsApp group name that you guys make for our class? Machine design. Because I have one, I rename it Machine Design 2026. Are you guys on that? Oh, that one. Okay. Okay, 20 members, including myself. Okay, is that the right one? Can you check?
Yes.
Yeah. Okay, I'm gonna change the group name to Machine Design 2026, so I'm not confused with the year. Who is not on the WhatsApp group? Anyone? No? Let's make sure everyone is in.
Ya, yang musik dari sini bawa ke Pertamina 10.000. Lebaran 10 masih cap dulu baru habis. Nah, berarti gue Bekasi dulu kan habis itu masih ada 50 kilo lagi. Masih cek polnya kalau kita jalan dulu. Special. Itu namanya special. Tambah 2 mili.
Kalau mulai
Benar-benar kalau main di sini kamu bayar.
Ini look, the wallpapers combined. The wallpapers combined. Cina dari sana apa? Oh, Cina Minang. Ini siapa tahu? Atau ada. Akhirnya nggak bisa di-repair. Del, kenapa temen lu, Del? Apa sebelumnya sih? Price-nya nggak kepikiran. Itu per berapa bulan? 12 gitu. Hah? 2 bulan? 2 bulan? Masa gitu ya 2 bulan? Tapi lagi bingung bulan ini soalnya pada banyak yang bonus sendiri. Kata gue ini udah tahu. Sendiri bisa. Gak boleh, terusnya gak boleh. Tapi Pak Pur nyaranin sama kita. Kalau saya didengerin lagi ini kenapa di sini? Roblox. Berapa dia? Sama. 250 di sini. Harga mesin motor sama kayak tempat. Alright, sorry guys, I was on the phone. Okay. After this point. We skipped some materials here. Okay, so let's talk about the shaft itself. When we design shaft, 2 things. First, we design it so it doesn't fail. So it's a stress or maximum stress that will cause yielding. You remember yielding? What is yielding? What is material yield? When you bend something, okay, when you bend something, it does not return to the original shape. That's when the material yield. Okay, that's considered failure, even though it's not breaking like literally tear apart. But once you bend something, for example, it does not return to its original length or shape. That's yielding. So shaft designed for stress basically do not yield the shaft. Second, for deflection, because sometimes your shaft might not yield, but it deflects up to a point where the function is disturbed. For example, consider like a wall fan, okay, for a room cooling fan. If the shaft deflects up to a point where the blade starts to touch the cage or the protective cover, then it becomes a problem, right? So you worry about 2 things, stress and deflection. We will not calculate deflection because it's very complex calculation, and start trying to spare you the math. Okay, so we'll do this one next week. I don't think we'll have time today. All right, now shafts are mainly made out of low carbon steel and not high strength steel, actually, because first of all, you want to machine it easily, right? And fatigue properties, this is fatigue here. We'll learn this next week, but basically the strength of a material to survive this fluctuating load is fatigue strength. And fatigue strength between low carbon steel and high carbon steel is not that much different. High carbon steel are the stronger steel. So, because in shaft we want fatigue properties. So that's why we go with low carbon. It's more ductile. And elastic modulus is also about the same. So we want a shaft that is actually, think of it as flexible, right? We want a more flexible shaft rather than a very tough, I'm not using the right word, very high strength. Because high strength tends to be brittle and it's not good with fatigue. Okay, we can surface harden when we use it as a bearing surface, but not always. Okay, so usually when you buy shafts, you start out with a hot rolled bar or a cold drawn bar. Hot rolled are usually rougher surface, more out of shape. Cold drawn are better shape, and they come with different diameter range. So cold drawn steel is typically for something less than 3-inch. So something like that is the biggest for a cold drawn steel. Bigger than that, you're gonna have to go with a hot roll. Okay, so usually larger sizes. But either way, both of them has to be machined. You know, when you buy stock materials, when they say it's 10 millimeters shaft, it's not 10 millimeters. It's usually something a bit more. So you can put it on a lathe and you machine it up to the diameter that you exactly want. Lathe machining is typical. Put it on a lathe. Everybody used lathe before? No? Did you go to ACME already?
No.
Ah, okay. So you will go to I think next year, right? You will go,
In a few months.
this semester.
Yeah.
Okay. You'll have some practical training with machineries there. For high production quantities, you'll use forming or casting. You can put components on a steel in different ways. So the axis here refer to the bearings. So you'll have gears between two bearings. Sometimes you can have pulley outside of a bearing. So these are the bearings, and this is the pulley for the belts. The reason you do this is so you can replace the belt easier, right? Because if it's here, then it might not be feasible. There are other components that you put on a shaft. For example, shaft collars. So say you put a gear here and you don't want it to slide axially, you put shaft collars in. These are basically split collars. You tighten these bolts, these two bolts, to clamp onto the steel shaft. For positioning, you can also use retaining rings. These are sometimes called snap rings. What you do is basically there is a groove. Okay, so if this is a bearing, you want to capture it there. You don't want it to pop out. So you put a retaining ring to actually hold it in place. Okay, the way you take it out is you can use a snap ring to extend or expand this. Take it out, and then it clips onto the groove. So on the shaft, you're gonna machine a groove like this. So if you look at it from the side, it's like that. Okay, and this groove is where the snap ring snaps on to the shaft. Okay, so it's often used instead of a shoulder. Something like this, you put on a clip, circlip, sometimes they call it there. When you want to join shaft to other components at the end, you also do these things. So let's say for this gear, you want to mount it on a shaft, on a plain shaft, then you put a set screw here. So this is the shaft, comes in, set screw. The shaft should also have some flat spot for the set screw to come in. So if you put this This is where it comes in. Okay, the set screw tightens onto that flat spot. If it doesn't have a flat spot, then you don't have a good contact. Okay, so you want a flat spot so it can transfer good amount of torque. This is called a set screw. I don't know what they call it in Indonesia. Bau tanam, maybe. So you tighten it. It has different endpoints. There are core points, oval, flats. Flats are the most common. Sometimes you have this, but if you have a pointed tip, you should also have that in the shaft. So set screws resist axial and rotational motion. They apply compressive force, create friction. The tip of the set screw may also provide slight penetration. Okay, but if you do that, you need to have the countersink on the shaft also. These are the common set screw sizes. It's called holding power. Set screws are not the most ideal way to tighten a shaft to a gear or to a pulley, but they are the most practical. They just slip on, you tighten it from the side, and it's done. Right? So these ones, this table gives you the size of the torque, the size of the set screw, and the holding power, or the torque you can sustain. Now, a stronger method to join a shaft to a component is called a keyway. So you see this prop that actually have a square notch on it, okay, like this, and the key also sit on a square slot on the shaft. Okay, so the shaft has a square slot. The hub has a square slot. You put this guy is called the key. It's basically a square piece like this. You put it there. This one slides on, and they lock each other. It provides a very strong way to transmit torque. Another way to transmit very high torque is spline, and this is what you have on your car, on the hub, when you connect the drive shaft to the wheel. It's constructed of these small grooves that fits on to the female side. Similar to that is a different type of spline. It's not the gear, okay? It's not a gear. Gears are very different. Even these are not gears. Don't call it gear. It's a spline. And I want you guys to practice using the right engineering terms. It's called a spline. Okay? So when you talk to vendors, please use the right terms. Unfortunately, I don't know the Indonesian word. We talk about shaft alignments. Okay? All right. Any questions on the quiz that I didn't discuss that you want to ask, just in case? Anything? Okay. Then let's redo the pretest.